All right. The title of my presentation today is Basics of Molecular Dynamics and its application for transport phenomena. All right. Let me introduce myself with a short biography. I graduated at Yonsei University in South Korea, and after that, I moved to United States to study further about the mechanical engineering, and I got a PhDs from Texas A&M University, and my academic advisor was Dr. Ali Beshkov and Tyler Chun. And after I graduated on 2009, I moved to Krasnow Institute for Advanced Study in George Mason University in Fairfax, Virginia. And I spent 2 years with Professor Abraham Blackwell, did the researches about the neuroscience. My job was modeling the diffusion of signaling molecules in the neuron cell. And after that, from 2011, I started working in University of Ulsan, and basically my research field is about the modeling transport phenomena using molecular dynamics, and I've been doing that like for 10 years. And this is my homepage website, and you can see my publications and all my lab student and my lab name is Micro and Nanoscale Thermal Fluid Lab. Okay. So my research background, I think I need to introduce that because what I'm doing is I realized that pretty much unique compared to my colleagues because I had two advisors when I was doing my PhD. One is Dr. Ali Beshkov, who's working on a micro and nanoscale fluid transport. So he's a CFD guy, and I did my master's with the spectral element method, basically a high order CFD method as well. So I was basically doing the CFD, computational fluid dynamics. But when I goes to PhD, I had another advisor actually from Caltech, moved to Texas A&M, and his name is Tyler Chun. He's from a multi-scale simulation method, and he's having a ab initio MD, molecular dynamics. So I learned the molecular dynamics from Professor Tahil Chun, and I learned the microfluidics and nanofluidics from Dr. Ali Beshkov. So I became to model microflows and nanoflows using molecular dynamics. And after that, I worked with Abraham Blackwell, as I explained. And Professor Murat Parashik in Turkey is actually lab mate when I was doing my PhD. And now he's in Turkey, and he and I are also making several publications together. And we are both working on nanofluidics using molecular dynamics. And for today, I'm greatly honored to have this opportunity to present my research, and I thanks to Professor Churodip Bakli and Professor Suman Chakraborty for inviting me here. I met them in a India-Korea joint research program for 3 years that has been started, I think, on 2018, and I had several chances to visit India as well, and it was a great pleasure to have research discussions with them. That leads to today's talk. All right. The first thing that I'd like to start with my research is great research is carried out with not just with the smart single person, but with the bright thought of a several generation. I cannot agree with this. No further. So I'm doing my research. I had recently has one of my PhD on 2017, and now he moved to the United States again, and he's working as a specialist in the United States Army. And I also learned from Dr. Ali Beshkov, as I said before, and Dr. Ali Beshkov learned from George Karniatakis. And all these knowledges that I'm continuing with, from my PhD is not just came out from nowhere. It has actually pretty much a long history that my advisor Ali Beshkov gave me this, and this is my academic family tree. And when I take a look at it inside, I could find many famous names in there, like Leonhard Euler, and Louis Lagrange, Denis Poisson, Laplace. All these names can be found in a textbook. And now I understand what they did in their time, and I realize that what I'm doing now is actually not that much different. At that time, these famous scientists didn't have the computers, and they have to use their imagination, and they have to solve problems with a pen and pencil. Now I'm doing something similar, not as great as they did, but I'm doing something with using computers. And when I see these academic family trees further, there are Dirichlet's as well, and there are Joseph Furios too. And let me explain why I'm saying that I'm continuing the work that they did. All right, so I think everybody is familiar with the Fourier's law of heat conduction, and that Fourier's law of heat conduction works very well in the continuum scale. And now I'm working on a molecular dynamics with a very small size, a confined. Right, I had a visitor. Wait. Um, all right, so Fourier's law is working very well in a continuum scale, but but people are questioning if the Fourier's law can be still valid in a 3 nanometer channel. Well, like an argon molecule, their diameters are like about 3 nanometers too. So 3 nanometer channel means that only a 10 molecule can be separated between the channels, right? So in such a small scale, like these molecules are visible, is the still the Fourier's law is going to be valid? That was my question, and actually that's one of the first paper that I published with Dr. Beshbog and Tayo Chun in 2008. What I did was I built a nanochannel separate with the 3 nanometers. I filled up with the molecules, make them a density as a liquid, and the one side I put a 110 Kelvin temperature, and the other side is 90 Kelvin temperature. So I put different temperatures to the wall, and I was successfully able to pull out the linear temperature gradient in between. So when I run MD, I when I get this linear temperature profile, and also I could get the heat flux directly from the molecules' position and their interaction. Well, with their relationship, I can get the thermal conductivity, right? So I get the thermal conductivity from the MD using the heat flux and the temperature gradient, and I compared that with the equilibrium method and the thermal conductivity value from the experiments and other MDs as well. It works, the values of the thermal conductivity is pretty much similar. That we are saying, even in a 3 nanometer scale, the Fourier's law of heat conduction is still valid. Probably the Fourier must have been thinking about that too, but I think he doesn't have any tool to validate his theories in 3 nanometer scale because he didn't have a computer and he didn't have a MD molecular dynamics tools as well. But I'm sure that he knew about it, and I think he had the visions about that too. And it took almost like 200 years to have it. Okay. All right, so basically my lab is using a molecular dynamic simulation method to do the model of the fluid compound in the nanochannels, and we are modeling the fluid transport and the thermal transport. Okay, so the first thing is let's start with the microfluidics and the nanofluidics. So typically when people talk about the microfluidics, you can think about the human hair. Okay, hair, typically the diameter is like from 100 micrometers to 50 micrometers. Thinking about the liquid that flows inside of that small pipe that the diameter is like 100 micrometers to 50 micrometers, the behavior of the fluid is pretty much different than the fluid that we see around, like a continuum fluid, because the surface tension and the wetting and the boundary slip is not negligible. But there are having some advantages too. Like in microfluidics with the flows in a scale of a human hair, they usually require a low energy consumption and the things could be built in a small scale. Okay. All right, so now we go much smaller scale and we need to talk with the nanofluidics too. So obviously the continuum fluid and the microfluidics are different, and the microfluidics and nanofluidics are different too. In addition to the small scales of the microfluidics, when it gets to the nanofluidics, actually we can see the molecule. Nanoscale is the molecules, the particle characteristic is pretty much visible. And the other thing is, until still the microfluidics, we can reach that scale with experimental tools. Like we can use a microscope, or we can watch it through the you know some kind of tools, experimental tools to make an observation. But when it gets to the nanoscale, it becomes very difficult to make an observation or make a modification or do some experimental treatment. So the molecular dynamics, having these molecules implemented in the computer and let them interact and make them visualize and see it through the computer, is pretty much viable approaches in that nanoscale. So and molecular dynamics becomes more and more popular as the computer develops more and more. So this slide tells us that the Nobel Prize in 2013, I was in University of Ulsan at the time, and I was pretty much impressed when they when I see the interviews that they made. And the most important sentence in here is what they say is, now the theory that we can build in the computer is pretty much an equal partner to the experiment. And the one day everything will be done by powerful computers. And I am also in a pathway of in the journey. Well, I'm looking forward to see the futures coming soon. All right, so now we're going to talk about the molecular dynamics and the statistical mechanics. Okay, so especially people who's interested in molecular dynamics with the liquid and confined in a small system. So molecular dynamics with the liquid, I really recommend this textbook, the best MD book that I ever read, and the most professional book that I ever found. And the most of the good paper that I read, even current day, they are citing this textbook. Okay, computer simulation of a liquid, MPLN, and the DJ tilde C. Well, this book explains a lot, but still, this is a kind of a difficult technique to learn. So today's my presentation is basically make a person who want to do the MD for their research, make them easily accessible to the MD techniques in a beginner's level, and that's my goal. And I'm doing my best to show the knowledge that I gathered from here and there about the MD. Maybe I can show you what it exactly looks like with some practical examples or the videos that I have in my computers too. Alright, so molecular dynamic simulation is basically we have a material in a molecular basis implemented in the computer, and in order to make them like a real material, we need to make them interact. Okay, so the easiest way to interact them is using van der Waals interaction. Van der Waals interaction is the molecular interaction between molecules with no charges, but even when they have no charges, we know that the electrons are flying or like they forms a probability cloud around the proton, and there are very instantaneous moments that the charges are not even neutral. So they can be modeled with the two rotating, very fast rotating dipole. And if you take the integral of a force interaction with the two rotating dipole, you can end up with having 6's power respect to the distance interaction potentials. Okay, so these repulsive forces can be modeled with the 12's power due to the computational simplicity. We can have a Lennard-Jones potentials that is mathematically very efficient, and it can mimic the van der Waals interactions with the proper parameters there. So here are more details of that. Once you have these intermolecular potential, and if you take the derivative respect to the distance, you are going to get the force. From the force, we get the acceleration. Every time step, we make the molecules move. And these are the parameters for this Lennard-Jones that is resembling the van der Waals of such a material. But these coefficients are actually decided to reproduce the bulk property of that molecule. Alright, so I explained the Lennard-Jones potential, and I know that a lot of presentations are just like that. They explain of the Lennard-Jones, but they never show what it really is. So I just want to make my presentations a little bit different than others. So I will show you something. The MD code that I made by myself. So let me change the screen to my own code. Here. Okay, now I think you are going to see one Windows application. This is a MD code that I built by myself with Professor Kyle Chun under his advice. I made it with the C++ code, and I can put one molecule there. This is argon, and it's just there, right? Because it's not interacting with anything else. And if I put one more molecule there, and actually one grid point is 1 nanometer, and I can run them, then they are interacting through the Lennard-Jones interaction. And this is a Hamiltonian system. The kinetic energy and the potential energy with that is pretty much conserved, so they will like oscillating forever. And what you see here is the blue line. Blue line is the kinetic energy, and this green line is the potential energy, and the line in between the black line is actually the total energy of the system. And I will talk about this later. The kinetic energy with a certain constant multiple will give you the kinetic temperature. So since the kinetic energy fluctuates, this potential energy fluctuates as well. The temperature fluctuates as well. So actually I can put more molecules and I can make them interact. Now this becomes an argon. Well, I say it's a vapor. Yeah. Depend on the density. So they interact. Now we have more molecules interacting through the 12-6 Lennard-Jones potentials. Now we have more molecule, and their fluctuation will be averaged. That the temperature and the kinetic energy fluctuation becomes less and less. Okay. So this is the not a real time, and it's real time in my computer, but it's every time step is a picosecond, so it's pretty much a slow motion of real argon gas molecule interacting each other in the space. Okay. All right. So let me go back to my presentation. So I show you how the Lennard-Jones potential interact, when we implement them in the computers, right? So we saw that. So these Lennard-Jones potential, their interaction strength and the diameter of the molecule is based on the empirical parameter, which is not really, not really 100% precise. But since people are working on quantum mechanics too, they can do all the energy equation to find the orbit and density of the electrons around the protons and neutrons too. We can build the molecules from first principles as well. And I have a Gaussian software, and I built the water molecules by myself. So oxygen and hydrogen and their charges. And when I solve this with the HF method, I can map the electron density and their charges in there. So this is the water molecule built from the ab initio, from the first principle. So if I have a more like a more of this cluster of these water molecules, it probably behaves like a real water, right? But the problem is then may takes like a huge computational cost, and it takes like forever, even if I run it like in the most advanced computer clusters that I had. But the interesting thing is, I could calculate the infrared spectrum and the Raman spectrum from this artificially built water molecule from the first principle, and I compared these spectrum frequencies with the experimental measurement. They are pretty much matching very well. So I say that these material that built in the computer is pretty much real, like behavior that they have. All right. Other examples that I like to give you is, so we have molecules interaction strengths, and from there, potential, the interaction potential, we get the force, and the force we get the acceleration because we know the mass of the molecule. From here, this is just the Newtonian mechanics. Okay. So once we have acceleration, we can update the velocity, and once we update the velocity, we can update the position. So using this Bellet algorithm, every position will be updated with their velocity and the acceleration, and the velocity will be updated with their previous velocity and accelerations as well. And in between, when we measure the acceleration, we need to get the force from the Lennard-Jones potential or other potential if you like to use in your MD simulations. Okay, so these velocity Bellet algorithm will make the molecules move, and I want to show you this as well. So I actually made the example code with this because some of you maybe want to build your own molecular dynamics code as well, like I did when I was doing my PhD. But even though I have my own molecular dynamics code, nowadays I'm using the LAMPS from the Sandia lab in the United States. They made a pretty much a good MD code, and that's very convenient to use. I'm using them, but still, those experiences that I build MD code myself, is helped me pretty much, it gives me a pretty much good intuition about the, about using that Sandia code as well, the lamps as well. So let me go to other application, right? Okay, so I already opened the code block. I don't know how the screen sharing will work with this, but let me just try. So code block. So now you see a typical debugger, right? Code block is free. You can do the C++ programming with this, and they support OpenGL too. So I will do very quick, okay? So I will do the new and the project. We can really start from the project, and I don't know whether you are seeing this small screen or not, but let me just continue because all you need to see is the result screen. They have OpenGL project options too. So I'll make the project title just arbitrary name because it's just the example, right? So when I go, I think you can see this one, right? They have a main C is here, so they pretty much give us all the basic code that we need to build And if you compile it and if you run them, they open a new window. A triangle is rotating. Let me see if I can show you that windows. Okay, share. All right, I can show. So now you will see a triangle rotating on the screen. This is the result. So this is pre-built. You don't need to do any coding. They give everything, and it's free. So this is a very good background to start the MD code of your own. So with this code, let me go back to the debugger. All right, here. So they have everything, right? And I have this code, and I already explained that the position. Okay, I will make it larger, and I will change the size of the screen to 4 times larger. Okay, and I will make this make this object to move. So the thing is, in here, I just add this code. Okay, so what I do is mx and my is my current position, and the vx and the vy is their velocity. And with that, if I update this triangle, they are drawing triangles in there. This triangle that you just saw that rotating is going to move. Okay, so in order to do that, I need to declare them in the preprocessor. So I make them a global variable, mx, my, position, velocity, acceleration, and time step is there. And I need to initialize them. So here, before the loops, I initialize them. Well, I don't need to do this, right? Okay, I can initialize them like this. And then finally, I make them move. So instead of this triangle, I use translate command to move them with the mx, my that I have in here. Okay, so now I compile this. I stop that, and then now I compile it. Yeah, it's okay. And when I run them, okay, and I will show you the result. This sharing is very difficult. Okay, so I will show you the result screen. All right, now you see that in a much larger window, this triangle is circulating, right? It looks same, but now I implemented the time iteration steps in there. Not exactly velocity ballet, doesn't have that detail, but this will move if I change the velocity. Okay, so now go back to my previous presentation. In here, so this is the position update with the velocity with the accelerations, right? I have a simple versions in there. And I put all the position and the velocity, I put them as a 0. So that's why it's not moving. But if I make them their initial positions, like this minus 0.5 comma 0, and I put the x direction velocity like that, and I will put some gravity, like acceleration, not from the Lennard-Jones, but accelerations too. And I will implement the specular boundary and the periodic boundary that I will explain in the MD, okay? So the first thing is I will copy this and I will put them in the code. Let me change the screen sharing again. Okay, so go to this. Okay, so this is the code block. So I will change their initial position like this and their accelerations too. And I will put the boundary conditions as well. Right here. So here, before I draw my triangle, I will have a this is specular boundary condition that I'm saying. Specular means it's reflective. So when the y position, the position along the vertical line, when it reaches to the bottom, it will reverse its velocity. So it will bounce back. And when it reaches to the right edges, it will disappear and reappear again from the left. That will be the similar to the periodic boundary condition. So this is just 2 lines. And with this 4 line, that's it. The rest is really, what's in there already, right? So when I compile this and now I run them, and you are going to see the result screen in just a second. I need to delete this rotate, okay, and the compile, and when I run them, okay, now I will share that result screen with you. Okay, stop, and all right, do you see these triangles are bouncing around, and it disappears from right, and it appears again from left, right? And at the bottom, when they bounces back, this is a specular reflection boundary, and the right and the left is actually a periodic boundary conditions. Okay, this is very important in MD, and I will explain you why in detail. And from this step is exactly, I could build my own MD code, and that's not really difficult, right? You need to have a potential, and you have a time integration step, and the computer, just every time step you generate their position, you are going to have the, MD result. Okay, so this is the flow chart of the typical MD code that I have, and probably the LAMP has a similar loop inside too. What they do is starting from the initial condition, and they do the loop, and they will just generate out. So what you see is the OpenGL screen display, but the LAMP's code, what they do is they make a file output. So the output has every trajectory, position, and velocity, and every time step. Usually the files are very huge. All right, so when we have molecules in a computer, and they are clustered, and they have their own velocity, the first thing that we need to pull out from that coordinate system is the temperature, and this explains us how to pull out the temperatures. Okay, basically the temperatures in the molecular system is their kinetic energy, but their velocity need to follow the Maxwell-Boltzmann distribution of particle velocities, because there's a random velocity distribution. They need to follow this, and if they don't follow these velocity distributions, because in a real world, the air molecules are flying around our room. Some molecules are faster than the average, some molecules are slower than the average. Most of the molecules pretty much near the average velocity. They are flying around, right? And in a computer, the molecules are moving around. They should be the same as well. Some are slow, some are fast, but their distribution need to follow the Maxwell-Boltzmann distribution of particle velocities. Otherwise, what we have in computer is not a real molecule behavior. So what we have a computer means nothing, because if they don't follow the real molecules behaviors, in our real world. So when these molecules in the particle system, then you implement it in your computer, follows the Maxwell-Boltzmann distribution of particle velocity, they are called local thermodynamic equilibrium. And in a 2008 and 10, when I submit my papers to the Journal of Chemical Physics, many reviewers, they ask us that the whole system that we build is satisfying this local thermodynamic equilibrium. Yeah, they asked us, and they also asked us to prove it. Because if they don't follow this local thermodynamic equilibrium, what we built in that system doesn't physically make sense. All right, so this is from the probability distribution. This is the mathematical procedure how to pull out the temperature. So here, 3/2 Boltzmann constant with the temperature is the kinetic temperature is equal to the kinetic energies of the systems, right? So from here, if we simplify this equation, we can get the kinetic temperature. But at this point, I myself had a question. Well, if this is the definition of the temperature, what is the classical thermodynamic temperature that we learned through the textbook, right? And I did some research, and from the Evans paper in 1989, I realized that, again, I explained about the local thermodynamic equilibrium, right, with the distribution. If that local thermodynamic equilibrium is satisfied, we assume that these two temperatures are the same. But if the system doesn't really follow this local thermodynamic equilibrium, we cannot really say this thermodynamic temperature and the kinetic temperatures are the same thing. That was very interesting. And this is how to pull out the pressures from the particle system. Basically, pressure is a force divided by area, but if you multiply that with the length, it becomes energy divided by the volumes, right? So the volume is the volume that we have, and the energy, like a previous Lennard-Jones system, we have a kinetic energy and potential energies, right? So if you change this kinetic energy with this previous 3/2 kT, and if you make them a universal constant, and if they have no potential energy contribution, it becomes the ideal gas law. Yeah, that was very interesting. It becomes ideal gas law. But so in a gas, ideal gas law works very fine. But if you go to a very dense system, now the potential energy is non-negligible. So when you try to calculate the pressure, you need to include the potential energies in that forms as well. And if you use the Lennard-Jones, and that will be potential energy of your systems too, and that's how you get the pressures from the system. Okay, and another important thing in a molecular dynamic simulation is we only deal with the limited number of molecules, and the people in our time always question how many molecules do we need to recover the classical thermodynamic property. Like one or two molecules, we cannot define temperature because we don't have enough statistical averages, right? So the ergodic hypothesis means the ensemble averages with the many spatial distribution is equal to the time average through the small molecule, make the evolution through the time, and if you average it, that's equal to the largest system. That's the ergodic hypothesis. And we are using this in an MD. We only deal with a limited number of molecules, but based on the ergodic hypothesis, we are dealing with a small number of molecules, but that can recover the thermodynamic properties of a largest system. Okay. All right. So periodic boundary condition and the specular reflection that I show you with the code block examples, right? So this is another way of dealing with a large system. In an MD, we only deal with a small number of molecules, but we put like a periodic boundary conditions around, and that the system will interact like with the surroundings, and it will behave like a large number of molecules that makes us to be sure that we have enough statistical averages. And when we need a boundary, we can either have a specular reflection or diffuse reflection. Specular reflection is very nice for the statistical confirmation. They can maintain their velocity distribution, but they cannot really control the temperature. But if you use a diffusion reflection, they reflect the incoming molecules with a certain distribution, but you will have and you will have controls over the temperatures. Okay. All right. So in a classical thermodynamics, pressure, temperature, and volume is very important. But when we deal with this molecule system, number of particle, volume, and energy, chemical potential, pressure, temperature is the most important thing. So when we run certain MD, we need to fix. We shouldn't change these numbers so that we can have a balanced system in a steady state equilibrium system. We need to fix this microscopic state. So if you fix number of molecule, volume, and energy, it becomes NVE, and it's microcanonical. And NVT is you fix the number of molecule and the volume and the temperatures. Okay. So it's essential to control the temperature of the system. After I explain this, I will show you how these isokinetic and Banerjee, like a velocity scaling thermostat, and there's a stochastic thermostat, Nojé-Hoover thermostat behaves, because I have an example code in my hand. Okay. So the first thing, this isokinetic and the Banerjee thermostat is velocity scaling thermostat. Basically, the velocity distribution, the average velocity of the molecule is the temperature, right? So if we make the molecules move faster, we will increase the system's temperature. And if we make the molecules move slower, we actually decrease the temperature. But the problem with this velocity scaling thermostat is it will destroy the local thermodynamic equilibrium if you do something applied from outside. Okay, so if you do the shear or if you make the flows happen, these velocity scaling shouldn't be applied in there. These velocity scaling thermostat is only good for generating the initial condition. But while you are running an MD simulation like a shear flows, pressure driven flow, capillary rise, you still want to maintain the system's temperature, right? In order to maintain the local thermodynamic equilibrium, you need to apply the stochastic Anderson thermostat, or I'll say the best thermostat that we can use ever for this state MD simulation is the Nojé-Hoover thermostat. Alright, so now I have this code that I built by myself, is in my hand, in my computer, it's available. Let me show you how these thermostats are working. Okay, so let me change presentations from my slide to here. So this is the three-dimensional MD code that I built. I hope you can see this clearly. All right. So when I put the initial condition with the molecules, you see that all the periodic molecules are around. This is now 3D, right? I can actually rotate them. I used OpenGL to build this. Okay. All right. So this is NVE system. Okay, NVE. Number of molecules are fixed. volume is fixed, and energy, you see the total energy, kinetic fluctuate, potential fluctuate, but there is no energy in or out from the outside surrounding, so their total energy, these green ball, are pretty much fixed. Okay, so now, but I don't have a really control over the temperature. Temperature, they're just fluctuating because their kinetic energy is fluctuating. Now I can make them stop, and I will apply the thermostat, the velocity scaling thermostat. You will see the molecule will behave very unnatural. And when I run the simulation, now, when I see the molecules are move faster, I make them slow. When they are slow, I make them faster. So the temperature are very specifically fixed to 100 kelvins in there. All right, and that means we are interchanging our energies from some outside surrounding, mysterious surrounding, hypothetical surrounding. So the total energy fluctuate. Only the kinetic energy is pretty much fixed. Okay, so this is the velocity scaling thermostat. And I can show you actually how I control the. So I turn off the thermostat now, and remove the periodic molecules, and So okay. So here I scale down their velocity. This system is pretty much like a frozen. I have a button there that scale down their velocity, and if I increase their velocity, you will see the molecule moves much faster, right? So scaling this velocity is key to scaling the temperature of the system. All right. So from the initial condition again, okay, initial condition. Let me show you the Nodze-Hoover. So I apply Nodze-Hoover and apply the random velocity distribution there, and when I run them, oh, they crashed. This happens. Okay, let me run them again, because I didn't do the exception, treatment inside of the code. I know why that is happening. Let me just do that one more time. Right there. Okay. So here, initial condition and the Boltzmann with the now Nodze-Hoover, and if I run that, okay, run that. This is how the Nodze-Hoover thermostat controls the temperature. You see, the temperature fluctuates around 100 Kelvin, but they have a lot of fluctuation. But in this way, we can maintain the Gaussian distributions, of the system. The molecule doesn't behave like a natural, but the good thing is we maintain the local thermodynamic equilibrium. If you collect these molecules at velocity, and if you map them to the distribution, chart, you will see their Gaussian distribution is pretty much well, maintained. Okay. All right. So this is Nodze-Hoover. Looks like it's difficult to see this with the lamps. All right. So let me go back to my presentation file. All right. So I show you how the thermostat velocity scaling and the Nodze-Hoover thermostat, actually make it how it looks like in MD. And when the time that we didn't have a computer, people are still solving it using Boltzmann equations, right? They know their molecules distribution through this, conservation equation. They could solve it, but that requires, I think, some kind of genius, to make this equation works, and also only could solvable for the binary collisions or with a lot of simplifications in there. But MD involves the Newton's equation motion of a molecules interaction. We don't really need the super smartness for solving the system. We just run them through the computer, let them interact and collect the data, and then we can get the thermodynamic property that we want. So MD, I think that's a kind of cool and easy, right? And the computers do all the work. And the DSMC, direct simulation of Monte Carlo, is very similar to MD, but what they do is they just create many ensembles, like random distributions thrown to the space, and they collect the MDs too, the thermodynamic properties. But these ensembles, like all the snapshot generated with the DSMC, doesn't really have a continuity in each snapshot. So I think they have a difficulties to pull out some force-dependent thermodynamic properties like viscosity. But they are good at pulling out the streamlines or something like that. That's what I heard. Okay. All right. So I show you how the thermostat works, and I show you the thermostat with the my code. But now even I'm using LAMPS as well. And I show you how to start your codings with MD, right? Time integration step using the C code. That's not difficult. But most of people using LAMPS, and even I use LAMPS as well. And for anyone who's interested in using lamps, I made the tutorials. Okay, so let me go to this website. Actually, this is my homepage. Maybe I can show you in this way from the browsing. Maybe it's better. So okay, here now you see the Explorer, Windows Explorer. Here, if you just type my name, then I have my homepage. You can go to the Scholars too, and they will directly will connect you to my homepage. Here in my homepage, they redirected it. Okay, so let me move to other window because they redirected it. So okay, this is my homepage, and if you go to the number 8 lamps molecular dynamics tutorial, I hope you can see this. All right, here I made a very simple version of the script. This script, if you just copy this and put it into the text file, okay, and download the lamps code and install it on your computer, and here is the all the command that then you need to put, and what file you need to read, and what you are going to see. I made the summaries in here, and I using this to train student in my lab when they first join. So even without they know what the molecular dynamic simulation is, they can already run the lamps with this. Okay. Of course, you will find this information in LAMP's web pages too. But once you go there, that's like a huge ocean, like too much of information, and it's very difficult to get familiarized with that. But mine are pretty much a simple explanation with the only necessary command. So I think this could be a good start. So hopefully this will be useful. Any of you who might be interested in molecular dynamic simulations, okay? And these are like a silicon and argons in between, and where to get the force field file and their script already provided in here. You can just copy paste this to text file, and using the lamps it will work. And all the command, this is like a minimum command that I use for lamps, and that they are explained in here. And once you familiarize yourself with this example and how to do the post-processing too, how to see this temperature profile, density profile. Once you try this, after that, I think you can go to lamps tutorials. Okay, and they have all the manuals in here, but they are like in a huge quantity, a lot of things that you need to read. So I think the my homepage example gives you pretty much a simple. It's just too simple. Like even an undergraduate student in my computer programming class can do that. So that will be a pretty much nice start. Anyone who's interested in lamps. Okay. So let me continue with my talk. All right, so far I briefly talked about the basics of MD and how it works, and I introduced you my code, and I introduced the lamps, and I introduced you the example script in my home pages as well. And I've been using lamps, and I've been using my lamps for a long time, and I made several publications. And let me introduce my researches from now on. Okay, so my research is basically focusing on the modeling solid-liquid interface, because these interface, the atomistic length scale plays a key role, and previously people were simply modeling these interfaces with the specular reflections or diffusion reflections. But now in these days, there are more needs for having a realistic interfaces with the realistic solid liquid interface, and the MD is a very good tool for that. So I already explained you about this, right? So I'm using two walls with the Fourier's law in a 3 nanometer channel has been validated. And in there, the differences in a 3 nanometer versus the continuum is they have a temperature jumps on the interface. So it was first discovered by the Kapitsa in 1941. That is called Kapitsa resistance. And my first work was using MD to model this Kapitsa resistance. And then I realized that these temperature jumps on the interface is the phonon frequency difference, the thermal oscillation frequency differences, and the wettings, and the wall temperature, and the temperature gradient. And we can apply the Nabia type boundary conditions to model that. And I published that on 2010 on microfluidics and nanofluidics. And after I moved to the University of Ulsan, this Ulsan is a huge industrial cluster in South Korea, and they are really interested in the manufacturing. And in year 2015, the additive manufacturing was so popular, and I was in part of that, and I had to model the local melting process in 3D printing. And you know that in a 3D printing, they use a laser beam to mold a very small part, and they do the additional additive manufacturing, right? So I did the melting and the cooling modeling using the MD, and I realized that the MD even can do the latent heat as well. When they melt and from solid, they absorb energy, but the temperature doesn't rise. That gives a peak of the specific heat value. And I was wondered, the solid that I built in my computer, are they going to have a latent heat? When they go through the phase change process, is the CP value will be infinite? That's what I wondered. And I run them with my student. Actually, the CP value was a peak, right? So I was so happy that my solid, the copper, this is copper or silver, I think, and that I built in my computer really works like a real material, right? Then I realized that my advisor in a Journal of Chemical Physics in 2001 already published that one, and these two figures are pretty much look similar. And I realized that I'm behind my advisor still like 20 years. Well, that was very cool anyway. But with other things, these with other data too. Of course, I cited them and I published on the Journal of Chemical Physics 2018 with the melting interface. Okay, so in order to model the melting interface, this is a solid and a liquid. When they form the melting interface, I talked about the Kapitsa resistance, right? There should be a temperature jump, but there was no temperature jump. And my student, actually, Dr. Bo, was very worried about it, and he comes to me and saying like, Professor, I should observe the temperature jumps on the interface, but I see no, something must be wrong my simulation. And I said that you shouldn't worry about it. There must be something very cool that we don't realize, because it's supposed to be not happening, and we did nothing wrong. There must be something new, right? So we researched it further and realized that all these melting interface is not specular and very smooth. These kind of diffusive structure actually gives us a overlapping of the phonon, and it gives a less temperature jumps. That's why even if we have a solid and liquid interface, we don't really have a temperature jumps. And this was a very nice work that we think published on the Journal of Chemical Physics in 2018. And after that, to apply to the additive manufacturing, like a 3D printing, we did the size-dependent melting point with these silver nanoparticles too. I show you many animations with my code, right? So now let me show you the video that we did this research. Okay, so that's my video files, nanoparticle. Okay, I will share this video with you. Right here, this video, hope you see this. So this is a nanoparticle. Some high temperature, I cool them down and see how the grain boundary happens inside of them. So I cool down. And then they crystallize from the liquid-like status. I run this simulation using MD and visualize it using Morbito. Yeah, so they crystallize like that. So this is an example of lamps. All right, let me go back to my presentation. Okay. All right, so these are basically heat transfer application, and now I do liquid simulations too. And the most biggest question is, how do we validate our simulation? So the material that we have a computer and we do this and we do that, how do we know it's real? How do we validate? Okay. All right, so this is pretty much interesting talks too. The first thing is, like I said before, when it gets to microdomain, surface tension, wetting, boundary slip, interface thermal resistance, chemical reaction is important. When it gets to the nanodomain, now we goes to the molecular level, right? So molecular interaction, structure, oscillation, molecular level reaction, and electron phonons becomes important. Okay, this is very great work in Nature, 1989. They dropped a small droplet of a PDMS liquid, and they see their spreading is like having some steps in there, because when they have a small molecule, they see these molecules are layered and they build a step like a structure, and this is called dynamic structuring. And even when in a physical review letter on 2001, when they have a water molecule near the interface, they will see these oxygen molecules have a peaks like that. And this is very strong evidence of molecules are layered on the interface. And when we run MD with the liquid with the solid interface, we should see that too, because the MD doesn't really reproduces what happens in the real world. There's no point of running it, right? So after that, there are many other works that experimentally tells us that there are layering of the liquid molecules on the solid surface because of the force interaction. All of them are showing that, right? So this is the work that we did. We have a gold and the silicon surface interacting with the water, and we run the MD, we see that there are layerings too. So our simulation, we just put the molecules interaction. The water molecule behaves similar to the experimental observations, okay? And then these layering is showing it as well, and we are interested in the interfacial thermal resistance, Kapitsa resistance with the wettings, okay? So in common sense, Kapitsa resistance will be decreased if you increase the pressure, because if you increase the pressure, you're pressing them hard, so the interaction between solid and liquid becomes increased, so there will be less resistance, okay? So if we increase the pressure, the Kapitsa length decreases in silicon. Okay, so this is pretty much a common sense, like a normal. But in gold, even if you increase the pressure, so since the increased pressure increase, the Kapitsa resistance, the interfacial resistance doesn't decrease. Why? Because in this case, wetting, the strong wetting already hold these molecules on the surface, so pressure doesn't really play an important role. So I'll say this wetting, that with wetting over dominant, this pressure is very typical phenomena in a nanoscale. Okay, and we published this on Journal of Chemical Physics in 2013. And these are the work that we published on Journal of Physical Review E on 2015. Capillary rise. There is already a Lucas-Weismann equation that can predict it, and this equation is actually updated with the slip length, because most of the microfluidics have slip characteristics on the interfaces, right? So we built that with the MD, and this equation should fit. This equation should be able to predict what their behavior. So we have this MD, with the copper and gold, and we have a water, and we make them rise is happening, and we apply the slips and the contact angles to the equations too. And when we plotted it, well, this equation doesn't really predict well. This dotted line is the predictions from the equation, but this is line with the dot is the prediction with the Lucas-Weismann equation. This dot is from MD, and when we see the result from our molecular dynamic simulation, the water rise much slower than this equation. So equation fails to predict it in nanotubes. So we are wondering why, right? But now we realize that this equation, this Lucas-Weismann equations, or even updated one, doesn't include the latest discovery. The people are talks about the layering, right? So they are layered on the interface, but this equation doesn't say it. So maybe that's where the miscalculation came from. So now we calculated the layering that causes the stress increase on the interface, and probably they causes the increase of the viscosities too. And with that previous equation, we already with the previous Lucas-Weismann equation updated with the slip length, we updated that with one more time with the considering the interfacial viscosities too. Okay, so with this updated viscosity, because of the layering, well, true behavior of the nanofluidics, and when we make the corrected prediction, they had a very good matches with the rise equation versus the MD. So these two prediction line goes down and the matches very well with this. So we published this on a physical review E, saying that when it gets to the nanofluidics in a nanotube, this layering and the interface of viscosity is very important. I published 2015. We got pretty much quite emails through that corresponding author's email address, which is mine. And they, one is from Germany, and one's from India. Actually, I think this is from Professor Chirodi, saying that they observed a similar thing. And after this email, I became to know many international scholars. I also had a lot of talk with this German scientist who's doing the experimental work, saying that they were also observed the reduced filling kinetics compared to the bulk expectation, and also from Francis as well. And this is that Professor Patrick Huber, who's do the experiment in a nanocapillary, saying that their experiment has a much slower filling compared to the theory, and they were also thinking that the local viscosity is plays a key role in it too. So we had a very nice talk, and I was almost spent my sabbaticals with them, but I changed my mind and I went to the United States on 2017 for my sabbatical. And these nanochannels can be made in with the crack lithography technique. Why I put this? Because one of my colleagues who's very expert in this kind of a technique is working neighboring university to mine. So we meet frequently and we talk a lot. And he gave me a lot of inspiration. All right, so like I said, the in addition to layering, these kind of late work, focuses on the local viscosities too. But probably the local viscosity doesn't pull much of a public attention. That's why it's a good publication, but not as great as a previous one, I think. But still, there are evidence of interfacial viscosity has been increased because of the interactions. Okay. All right, so these nano drumlet is also very useful, cases for the molecular dynamic simulation, because wetting is also a huge issue as well. It has a lot of application. So the reason why I show you this wetting contact angle MD is this is a very popular example of lamps as well, and I think I can show you that too. I have it here. All right, so I open that. Let me switch this to that one. Okay, so this is I have a copper and the graphene sheet, and I put a water drumlets in there, and this is the typical lamps, you know, MD looks like. And we can add one graphene, two graphene, three graphene, and we could see how the contact angle changes. And from the start with the one graphene, they are likely a copper surface. But as I put more and more graphene in there, they behave like a contact angle in the graphite. And why this application is important? The interaction strength between solid and liquid is pretty much passive, and we cannot really change them. But now we have a graphene. By adding one or two or three, we have a control of the interaction strength between the liquid and the solid, and I think that's a cool thing. All right, so stop this video and go back to my presentation. All right, so time's almost up. So we can do the shear flow modeling with that as well. And the next thing is we are doing the nanopore modelings too. So nanopore MD, as you see in here, simple fluid goes through the pore, and we have modeled it and compare it with the continuum models as well, which is called Sampson's flow. And we published this to Physical Review E. This local viscosity and the position of the boundary is also important for the predictions as well. And the next thing that we want to go with this is the desalination. Okay, we put the ions in the water, and we like to find out the key factors to decide whether ion passes or not. And that's ongoing work. And the more complex problem is with the ions. We can do the electrical double layer modelings too that we are currently working on, and we can do that in the MD. This scale with these ions are almost impossible to reach with the experimental technique. So MD is a very good tool for that. Okay. So these are our current work, and eventually, with all this, where am I going? What's my research interest? Currently, I'm funded from the Korean government, and the Korean government are pretty much interested in a hydrogen fuel cell. And when you take a look inside of the hydrogen fuel cell, there are like a lot of molecular transport phenomena. Like even the channels are in a micro scale, and most of the ions are diffused, right? And the MD is very good tools for modeling them. And my idea was when we see the IC chips, like the memories or something, they start from the the vacuum tubes. Now they are in the integrated circuit, like in nanoscales, right? And these hydrogen fuel cell or other fuel cell energy systems should be in a chip scales already, but we are not really get there. The technology is still like in a vacuum tube scale. Why? Because we don't really solve the problems with the fluid flow, like the wettings and surface tension that makes these systems and flow not working if we make this a nanoscale. So using MD, if we can solve this problem and find a way to drive the mass through this nanoscale channel, one day all these energy systems will be as small as a computer memory, and I think that will change our lives a lot. Okay, all right, this is what I have for today, and these are my crew members. Some of them are left and some of them are new. I haven't updated that, but they are very nice friend of mine, and they are very nice research fellows, and I'm very happy to work with them.